Hi everyone, in this segment we are going to be talking about acid-base equilibrium, okay? Equilibrium is this idea that we are at a steady state for the reaction, where the opposing reactions are balanced energetically to favor the side with the most stability, meaning there is a back and forth and a back and forth that occurs in an acid-base reaction, and equilibrium is reached when that back and forth has reached that most stable state, the steady state, okay? And it could be the case that one side is favored over the other at equilibrium, or there's an equal amount of these species and these species at equilibrium. Really depends upon the reaction that we're looking at. I think the crux of the matter here is that when it comes to acid-base equilibrium, we can think about the side that is favored at equilibrium will have the higher pKa acid. Okay, so for instance, in this example, this side is favored at equilibrium. This side has the higher pKa acid, pKa 9, as opposed to the acid on this side, which has a pKa of 5. Okay, so again, to repeat that, the side that is favored at equilibrium will be the side with the higher pKa acid. And I really want to stress that this is the side with the most stability. Not only is this the side with the weaker acid, we would say that if you were just to compare the bases, right? This is the side with the weaker base. So here we have the weaker acid, the higher pKa acid, and we have the weaker base. But I really want to stress that this side is the more stable side, and that is why it's favored at equilibrium. For your purposes, you can think about weak and stable as being synonyms. They are synonymous terms, even though in the English language those two words don't really connote the same thing, right? When I think of the word weak in English, I don't think stable. So it's a little counterintuitive, but that is how we can think for acid-base chemistry. This side is favored at equilibrium because there is more stability. So just to really stress this, in an acid-base reaction, there is a back and forth. We could imagine on this side, these two species interacting. The base removes the proton, and we form the two conjugate species. But then there's a back and forth. So your NH3 could remove the proton, and then we would deprotonate to form these two species again on the left. There is a back and forth and a back and forth. And in solution, all four of these will be present. I know we use our equilibrium arrows here, right? Kind of our half arrows to describe this. It's not that we either have this or that we have this. In solution, all four of these are present. However, there will be a higher concentration, a greater prevalence of these species at equilibrium because they are ultimately more stable than the two species existing on the right side. Okay, and I think that's what gives a lot of people trouble, is we think about this in too much of a black and white type of scenario where it's either this or we have that. But the reality is all of these are present in solution at equilibrium. And the extent to which we have those species present is a function of the difference in the pKa values and the difference in stability. So here you would probably have a lot more of these two species than these two species, but you could probably find those in a really small concentration. Okay? Equilibrium is a dynamic back and forth. However, at equilibrium, there is a steady state where there will be a side that is favored if there is a difference in your pKa values for the acids on each side. And again, just to reiterate one more time, the side that is favored at equilibrium will be the side with the higher pKa acid. And that side has both the weaker acid, the higher pKa acid, and the weaker base. And those two species, our base and acid on this side, are more stable species than the conjugate species on this side of the equilibrium arrow.